Okay, so let's get started then. So welcome everyone. Welcome to another RISC-V technical session. This is the second session of this year. And today it's my pleasure to introduce you Andrea Bellano from University of Bologna. Andrea holds both bachelor degrees and a master in computer engineering and is currently pursuing his PhD in microelectronics, focusing on hardware acceleration for AI applications. Today, he's presenting a transformer acceleration template, leverage the PULP cluster, and a novel technique for optimizing Softmax and GELU operations. So please welcome, join me, welcome Andrea Bellano. So Andrea, the floor is yours.
Okay, so let me share my screen. And okay, here we are. So, yeah, hello everybody. And wait a moment. Okay, hello everybody, and thank you, Rafael. So today I present my work on the acceleration of non-linearities in transformers. But before, a brief introduction about myself. So I received the bachelor's and master's degree in computer engineering at the University of Bologna in 2022 and 2024, respectively. And this October, I started a PhD in microelectronics under the group of Professor Luca Benini, which is PULP, as you can see from the template of the slides. Now, in my research, I focus on the acceleration of artificial intelligence applications on energy efficient platform. And since we're talking about artificial intelligence, we cannot talk about transformers. Now, this transformer is the main model driving the evolution of modern artificial intelligence, and is both in perceived tasks and also, and most importantly, in generative applications. Think about, any large language model. However, this huge performance uplift comes at an hefty cost, both in terms of parameters and also layer complexity, because transformers in generally use much more parameters than previous generation neural networks. Think about ResNet, which used around 25 million parameters, and then the base vision transformer, which uses 600 million parameters. So yeah, they are order of magnitude more. And also, a single layer of a transformer is much more complex compared to the layer of a CNN, for example, because it features the multi-head self-attention and also additional projections. Now, state-of-the-art models are huge. They use often more than 1 trillion parameters, which makes edge inference unthinkable, because we are not even remotely near the required performance and memory capacity on embedded devices, which makes cloud the only choice for these models. However, there's been significant interest in running smaller models, so 1 billion parameters or less, at the edge. And this is because there are, for example, applications that require low latency, such as robotics, where we cannot afford for a server to perform the inference. And another self-explanatory reason is to reduce wireless traffic congestion. And another very important reason is to improve privacy and security in generative AI applications, because with generative AI, we are possibly sending our personal data to a data center, God knows where they perform God knows what with our data. And so if we perform inference on site, well, we just avoid all these problems. But now, since we want to run transformers at the edge, we may think about quantization. And in CNNs, this is the standard, and for a good reason, because quantization really cuts the model size, because we are using very low baseless parameters. It boosts inference speed and efficiency, since we are inferencing in fixed point formats normally. And also, on top of that, the performance of a quantized CNN is comparable to the performance of the original model. So we really do not have any reason to not to quantize a CNN. However, with transformers, it's a bit more complicated, because they are orders of magnitude more expensive to train compared to CNNs, and they are often trained on huge non-public datasets, or even with human feedback, which makes quantization over fine-tuning often impossible. And on top of that, activation quantization is still not mature. So we cannot expect a quantized transformer to run like the non-quantized model. So quantization is often not feasible for transformers, and for this reason, we focus on the acceleration of transformers out of the box, so in their native format, which is, for the majority of the models, befloat 16. Now, to accelerate transformers at the edge, we use our template, the PULP cluster template, which features 2 to 8 RISC-V digital signal processing cores, which acts as a shared L1 scratch-on memory, the tightly coupled data memory, TCDM for short. This memory features bulk interleaving, which means that all cores can access the memory as long as they access different memory bands, which has the effect of increasing the throughput by a great degree. Now, we also have 32 kilobytes of shared instruction cache. And finally, we can accelerate specific tasks in 2 ways. One is to exploit the flexibility of the RISC-V ISA to extend our instruction set architectures with specific instruction. And we can also instantiate cooperative array processing engines, so accelerators that share the TCDM with the cores, making them tightly coupled. Now, for accelerating transformers in particular, we will use 8 cores RISC-V cluster, 8 cores RISC-V cluster with 8 RISC-V 32-bit cores, which feature a 4 stages in order pipeline, the XPULP extension featuring hardware loops, bit manipulations, and SIMD, and since we are targeting floating point transformers, also a private floating point unit, supporting floating point 32 and befloat 16 formats, with the possibility of enabling two-way SIMD for befloat 16. Now, to store activations and weights, we also have 256 kilobytes of TCDM split among 32 bands. And finally, since transformers are computationally dominated by matmules, we also have a tensor processing engine based on the RedMulE architecture. In particular, this tensor processing engine is basically a systolic array of FMAs that exploit the outer product strategy. Now, let's test our cluster on a real model. In this case, WIT-based. And since we are only accelerating matmules, all other nonlinearities are just approximating using the fastest possible method. So we are disregarding accuracy for throughput. And we see that enabling RedMulE in a relatively small 12x4 configuration has a huge impact on performance with a 12 times throughput uplift. However, we see that once we enlarge our systolic array, the returns are clearly diminishing. And we see that something's wrong even in the utilization of the tensor processing engine, which is as low as 31% with the largest configuration. Now, clearly, something's wrong. And from the relative runtime, we see that when matmules are aggressively accelerated, the system is actually slowed down by nonlinearities, which become the main bottleneck in the performance in the throughput of the cluster. So yeah, we have to do something about them. But what are these nonlinearities? Well, let's take a look at the attention mechanism, which is the main accuracy boosting feature in transformers. And we see that it consists of multiple matmules, which we are good at, but also softmaxes. And like CNNs, softmax in transformers, softmax is applied multiple times every layer. And because we see that here we are applying softmax to multiple matrices, which means that if we want to accelerate transformers, we also have to do something about softmax. But what's the deal with this function? Well, we see that, first of all, it is based on the exponential function, a transcendental function that we'll have to accelerate or approximate in some way. And then we see that this is not a pointwise function, because first of all, for numerical stability reasons, we have to subtract the maximum input to every input to prevent the exponential from overflowing. And then we see that we have this nice summation in the denominator. So regarding the exponential, let's see how it is normally calculated by looking at GELU's exponential function. Now, this is clearly not an implementation. This implementation is clearly not suitable for low-power applications, later on hardware accelerators, because you see we have lookup tables, high-order polynomial approximations, and despite being the floating point 32 version, everything is computed in double precision. So yeah, we need an alternative to this function. And well, there are many alternatives. For example, we have Cordic, an digit method, which has a good accuracy and is also very efficient. However, its convergence is low, so it's clearly not suitable for a throughput-oriented accelerator. Then we may take a look at lookup tables, because they perform no computation at all besides the interpolation. However, since we are storing the every possible value of the function, they are costly in terms of area, and they work best with limited ranges, obviously. Then we may use polynomial approximations. And they are interesting because, thanks to Chebyshev polynomials, we can build optimal approximations in a minimal sense, at least. But again, for a good result, with polynomials, we must limit the input range, or use very high-order polynomials, which we want to avoid. So, are there any other methods? Well, actually, yes. There is Schraudolph method. Now, with the Schraudolph method, we have to think a bit outside the box. First of all, floats are stored as a sign bit followed by the exponent bits and finally the mantissa bits. And the value of a float is found as -1 to the power of the sign times 2 to the power of the exponent minus the bias, in this case 127 with before 16, times 1 plus the mantissa. So if we take an integer number, add the bias to it, and then replace the exponent with this number, what we get is a perfect base-2 exponentiation of the input. So yeah, we are clearly up to something, but two questions arise. First of all, what about the natural exponential? Well, this is easy. We just have to multiply the input by the base-2 logarithm of e. However, there is another question. What if the input is not an integer? Well, let's see what happens. So we do as before, but now the input is a fixed point number. So we add the bias, which will be also a fixed point number this time, and now we left shift the number until all its integer bits spill over into the exponent bits of the chosen float point format. And if we take a look at the value stored inside, we see two things. First of all, the integer part is perfectly exponentiated, as before, obviously. But regarding the fractional part, this is a bit different. We see that the fractional part replaces the mantissa. So what we get is actually a linear interpolation of the two nearest integer powers of 2. So we basically have a lookup table with linear interpolation without storing any value beforehand. So yeah, this is good, but still the accuracy is not so good. Well, to address this, Schraudolph proposes to add a constant to the result, which basically, as you can see, shifts the function to minimize the average error. Now, this comes for instance implementations, because we just add this constant when we add the bias. And from now on, every software implementation of this algorithm that we'll use this enhanced version. However, in hardware, we can do much better than this. Because since the integer part is always perfectly exponentiated, we can increase the accuracy of our approximation by processing the mantissa only. And in particular, we propose to replace the fractional part of x with a polynomial of it that in some way approximates 2 to the power of the fractional part of x. Now, our polynomial is defined as a piecewise second-order polynomial, and in particular, we split the 0-1 range into 2 halves. In the first half, we approximate 2 to the power of x minus 1 with a straight line tangent to it in 0 and a parabola centered in 0. And after a simple transformation, we get the final form of this polynomial, which is a constant times x plus a constant, which is extremely easy to implement. Now, regarding the second half, we do as before, but now the functions are centered in 1. And after some transformation, the best we can do is this. So yeah, it is similar to the first function, but we have this 1 minus something that, well, they complicate the evaluation a bit. And it would be nice to have this function look more like the first. And actually, if we approximate 1 minus x with x1's complement, we see that the evaluation of this function is simplified, and we have a function that is very similar to the first one. But we are still not done, because in practice, we replace the additive factors with 2 free parameters, gamma 1 and gamma 2, and optimize them independently. To place the parameters, we use a Monte Carlo procedure, and Monte Carlo procedure to find the parameters that minimize the error introduced by the approximation. Now, the final parameters have a very low bit width, in particular only 4 bits for alpha and beta, and only 8 bits for gamma 1 and gamma 2. And if you look at the implementation of our exponential unit, you see that it is also extremely simple. So now that we have our exponential unit, let's see its accuracy. And well, the average derived error is just 0.14%, which is 13 times lower compared to Schraudolph, with a relative accuracy of 99.86%. And regarding maximum error, this is no greater than 0.78%, which is 3.7 times less compared to Schraudolph. And in Bishop-16, this translates into an approximation that is wrong just 25% of the times, and when it's wrong, it is just 1 unit of risk precision away from the correct result. So now that we have our exponential unit, let's see how do we accelerate Softmax. And to do so, we introduce SoftEx, a parametric accelerator of Softmax on Bishop-16 vectors. It is organized as an hardware processing engine, so we have a streamer to access the CDM, a control fine state machine, and obviously a data bus, which features n lanes, each containing a multiplication and addition unit and an exponential unit. And also, we have a single accumulator module containing a pipelined floating point 32 fused multiply add. Now, to compute SoftEx, we split it into 3 steps: the accumulation step, the inversion step, and the normalization step. During the accumulation step, we compute the denominator of Softmax, as the name suggests, and in this step, every cycle, we read an input, subtract them the maximum score, exponentiate them, and finally push them into the denominator accumulator. Now, to avoid an initial maximum search, we use a random normalization scheme, in which the maximum score we are subtracting is not the global maximum score, but the local one. And when we find a new maximum score, all we have to do is to rescale the partial sum stored into the accumulator module by e to the power of the old maximum minus the new maximum. And once we are done, we have the exact same denominator we would have gotten if we knew the maximum score beforehand. So now that we have our denominator, we can start the inversion step, during which, as the name suggests, we compute the inversion of the denominator. In this step, we use the floating point 32 FMA to compute the reciprocal using 2 Newton-Raphson iterations. And the initial estimate for this method is found in the following way. Now, regarding the exponential, the exponent, we can find it by simply inverting the formula for the evaluation of floating point numbers, which yields 2 times the bias minus 1 minus the exponent. While regarding Mantis, we estimate it with a simple parabola. And so, after the 2 Newton-Raphson iterations, we get a very good approximation of the denominator. So we can start with the final step, the normalization step. In this step, we read the vector again, subtract the now global maximum score, exponentiate the result, and finally, the exponentiated results are pushed again into the multiplication addition unit and multiplied by the inverted denominator to be normalized. Now, during this step, since we are both reading the inputs and writing the results, we actually alternate the load of a new vector of n scores and a store of n results in an alternate fashion. And in this way, we can we can fully utilize the bandwidth in every step of the computation. Now that we have our soft accelerator, we are done, right? Well, not exactly, because if you look at the attention layer alone, yeah, there are no major non-linearities left. However, there is still the feed-forward network. And while in the transformer, they simply employ ReLU, modern models usually forgo this function in favor of more complex activation function. And one of them, which is commonly used in any high-performance model, is GELU. Now, GELU stands for Gaussian Error Linear Unit, and it is an activation that consistently outperforms ReLU across, well, every task, basically. Now, instead of getting the input like ReLU, the idea of GELU is to weight it by the value of the Gaussian cumulative distribution function. And obviously, we are not going to compute this integral. We'll need an approximation. And luckily for us, the authors of the original paper proposed 2 approximations. One, which is based on the hyperbolic tangent, that, as we can see, it is still a bit complicated. And one that is more simple, this is based on the sigmoid function. Now, good news for us, both the hyperbolic tangent and the sigmoid function are based on exponentials. However, they also both require a division of the terms. So yeah, instantiating a divider is out of the question in our design. So we will need another approximation, one that is possibly solely based on exponentials and basic arithmetic. And there is one such approximation. However, we have to focus on the complementary Gaussian cumulative distribution function, the Q function. Because for this function, there is an alternative formulation, Kreis formulation, that for positive arguments, that stands for positive arguments. Now, Kenny and others propose to apply the rectangular integration formula to Kreis formulation to get a tight upper bound of this function, and this upper bound is exactly a weighted sum of exponentials. So it's exactly as we want it. Now, we see however, we see that Kreis formulation only stands for positive inputs. However, we see that since this formulation can be shown that is symmetric, for negative inputs, it actually evaluates the Gaussian cumulative distribution function. So we basically have an approximation of phi, the Gaussian distribution function, cumulative distribution function for every for every input. However, this is still an upper bound, and it would be nice to have an approximation of this function. And lucky for us, Tanash and Rion propose a method to optimize the MB parameters by solving an optimization problem. And the resulting approximation optimizes the relative error in a min-max sense, and also its convergence is quickly. We only have to choose the number of terms and the range in which we approximate the function. So now that we have an approximation of GELU that uses a sum of exponentials, so it does not use dividers, we can send SoftEx to support it. Or better, we only send SoftEx to accelerate the sum of exponentials, because the remaining simple steps, so squaring x and multiplying the input by the Gaussian cumulative distribution function, are delegated to the course. And that's because we didn't want to complicate the design too much. So by accelerating only the sum of exponentials, the design only needs little modifications. In particular, we only have to add two buffers, one for the A weights and one for the B weights. And also we need one lane accumulator per lane, which, as name suggests, it is the one that computes the summation. Now, an interesting thing is that the accumulators are not for fused multiply adds, because since the accumulated value is bounded within the 0.5 range, we don't need the whole range offered by floating point numbers. We can just use fixed points. The only thing we have to decide is how many bits to use to represent this value. But first, we have to choose where to optimize this, where we'll typically optimize this function. And now we actually need a approximation that is accurate near zero and just good enough far from it, because after all, GELU behaves similarly to ReLU, far from zero. So we only need a good approximation near zero, where GELU is mostly different from more different from ReLU. So we decided to approximate the function for inputs whose absolute value is less than or equal to 2.8. And this is because for inputs greater than 2.8, the value of GELU in below 16 is exactly the value of the input. While for inputs less than minus 2.8, the value of GELU is so small that can be safely approximated with 0. So now that we know where we'll optimize the function, let's determine the optimal number of bits to be used in the accumulator. Now, for this, we swept both the number of bits and the number of terms and evaluated three metrics. One is the percentage of library mismatches on width on imagined one key, where and we use as a baseline a model where the non-linearities are not approximated, so they are computed with accurate methods. Then we measure the mean squared error of the logits, again on the Vision transformer, and then we measured the perplexity on GPT-2 on the weakest benchmark. Now, we see that using 10 or less bits is not sufficient, because it results in significant deviations that even get worse as we increase the number of terms in the sum of exponentials. However, we see that instead with 11 or more bits, the deviation stabilizes at around 4 terms. So, with a 14 bits accumulator and a 4 times sum of exponentials, we see that we achieve very good results. In particular, a deviation of just 0.27% on the Vision transformer on imagined one key, and a near zero mean squared error, and also a perplexity on GPT-2 that is only slightly higher than the base model. Now, as a comparison, an approximation that uses Schraudolph method and the hyperbolic tangent approximation for GELU achieves a much higher deviation on the vision transformer, while just a marginally better perplexity on GPT-2. So now that we have accelerated every measure non-linearity, let's take a look at the final test system. So as I said before, it features 8 RISC-V cores with the X-Parve extension and a private FPU, 256 kilobytes of TCDM split among 32 bands, 32 kilobytes of shared instruction cache, plus we have 2 hardware processing engines, the RedMulE tensor processing engine in a 24x8 computing element configuration, and finally we have SoftEx, a Softmax and GELU accelerator in 16-lane configurations. Now, we implemented the cluster in Global Foundries 2 nanometer technology and benchmarked it in typical conditions in 2 operating points. One at 0.8 volts for maximum performance, where the cluster reaches a frequency of 1.12 gigahertz, and one at 0.55 volts for maximum efficiency, where the cluster instead achieves a frequency of 460 megahertz. Now, SoftEx area occupation is extremely reduced, just 0.039 square millimeters, which is roughly 3% of the cluster area, or 1/6 of RedMulE's area. Now, if we take a look at the area inside of the area breakdown of SoftEx, we see that its area is dominated by the other 3 and the multiplication addition units, which together account for more than 40% of the total. Instead, we see that the expansion units only account for 10% of the total, so they are pretty small, and the line accumulators, which we specifically added for supporting GELU, only account for 12% of the total. So in the end, the cost for supporting GELU wasn't so high. Now, during Softmax, the cluster draws 278 milliwatts of power at 0.8 volts, or 56.1 milliwatts at 0.55 volts, with SoftEx accounting for less than 20% of the total, with the rest dominated by the SRAM banks. Now, inside SoftEx, the multiplication addition unit dominates the power consumption, with a contribution of almost 1/4 of the total, while the expansion units only contribute by 13.7% of the total. So they are much more frugal than the multiplication addition unit. Now, to test the performance of SoftEx, we used multiplications from MobileBert, and we see that even with a short sequence length of 128, SoftEx achieves huge speedups and energy gains compared to the cores, with a 6.2 times higher throughput and 15.3 times higher energy efficiency compared to a software implementation using Schraudolph method. And if we increase the sequence length to 512, we see that the gap with software increases even more, with a 10.8 times speed up and a 26.8 times better energy efficiency. Now, we also test the software implementation of our algorithm, and we saw that on average is 31% slower than Schraudolph method, but remember, it features a much higher precision. Now, regarding GELU, during some exponentials, the power of the cluster is more or less the same, with SoftEx again accounting for less than 20% of the total. But what changes is SoftEx power breakdown, with the line accumulators, now dominating the power consumption with a 22% contribution, with the multiplication and addition unit close behind at a 20% contribution. And doing some exponentials, we also see that the expansion units have a slightly higher contribution of 16%, but this is obviously due to their higher utilization. Now, to benchmark the performance of the cluster on GELU, we use this first feed-forward network. And we see that we compared SoftEx assist GELU, which used 4 sums exponentials to approximate the Gaussian cumulative distribution function. And we compared it with a software implementation using the similar approximation and Schraudolph method. Now, even if partially performing software, in the end, our decision of only accelerating the sum exponentials paid off with a 5.11 times speed up and a 5.29 higher energy efficiency compared to the software implementation. Now, to see if SoftEx effectively alleviated Softmax bottleneck, we test the system on mobile burst attention layer, where the bottleneck is solely due to Softmax. And we see that thanks to SoftEx, we reach a peak throughput of 324 gigaoperations per second, which is up to 2.17 times higher compared to the fastest software implementation. And using SoftEx also increases the energy efficiency by a lot, where in fact we reach up to 1.30 tera operation per second per watt, which is 75% higher compared to the most efficient software implementation. And from the relative runtime breakdown, we can see why we are so fast and efficient, because the relative Softmax runtime is reduced by up to 4 times compared to the best software implementation, or well, the fastest software implementation. So, okay, SoftEx clearly alleviates the Softmax bottleneck, but what about a full model? Well, let's see on bit, where the bottleneck is shared between Softmax and GELU. So, at 0.8 volts, we reach an average throughput of 310 gigaoperations per second, with an average latency, an average end-to-end latency of 113 milliseconds. Now, using SoftEx increased the throughput by 1.58 times compared to running the model using software only Softmax and GELU. And we see that to achieve this throughput, accelerating GELU was fundamental, because it yielded a 1.30 times 1.48 times speed up compared to a software-only GELU implementation. And regarding the energy efficiency, at 0.55 volts, we reach an average efficiency of 1.34 teraoperations per second, which is 1.42 times better compared to the most efficient which is 1.42 times more efficient than the best software implementation. So, to wrap this up, today we presented a flexible acceleration template for transformers at the edge, based on an 8-core RISC-V cluster augmented with a 24 times 8 computing elements tensor processing engine, and SoftEx, another accelerator for visual sensing Softmax and GELU nonlinearities. We saw that using SoftEx boosts the system throughput by 1.58 times and its energy efficiency by 1.42 times on the vision transformer, achieving 310 gigaoperations per second at 0.8 volts, or energy efficiency of 1.34 teraoperations per second per watt at 0.55 volts. And so we can say that SoftEx successfully achieves its design goal of alleviating the Softmax and GELU bottleneck. And with this, I guess that's all. Thank you for your attention.
Thanks a lot for your presentation, Andrea. So, folks, if you want to ask questions verbally, raise your virtual hand, and I can allow you to speak. But we have one question in the chat. Is about, so I'm not sure if I'm going to pronounce her name correct, but you're Lefteris. Sorry if I not pronounced it correctly. He asking about, so he completed his PhD, if I'm not mistaken. Yeah, he is willing to pursue a PhD in this field. So he asking for some advices on how he could, start the journey or get started to his as part of his PhD journey in this area. So any advice for him?
Okay. Well, okay, I didn't expect this question, but so any advice? It's well, it's actually the same for any PhD, because it's more it's choose your supervisor wisely, because okay, you may be doing a PhD in a very good university, but you work for many years with your supervisor. So it is fundamental to choose someone that possibly you know, and that you work well with. And yeah, regarding the field of microelectronics in particular, well, I don't have, unfortunately, I don't have anything more specific to say, because also because I just started after all. So yeah, I don't have much experience. Sorry.
Okay, so let's see if I have more questions here. Oh. Discussion about that. So that's one question that I have to. Well, within RISC-V, we are working on the two extensions, AME, attached matrix extension, and integrated matrix extension.
Yeah.
Do you believe, or do you have plans to start measuring that or prototype that and start to do some analysis about integrating that kind of instructions as part of this workflow somehow?
Well, unfortunately, at the moment, still not. We are actually now working on supporting the quantization on our designs. However, yeah, it would be interesting also to explore to explore this. So yeah, I think that's about it. But yeah, we'll definitely consider it, since our group is very active in the RISC-V environment after all.
Yeah, another question I have. So, do you plan to get a more, I would say, powerful board somehow and do another test, something like that?
Yeah. Okay. Yeah, a more powerful board. Our group is more focuses more on low power designs, but yeah, there's been some work on support on let's say supporting more powerful designs, but so it's more, so in the future we'll most likely also explore this. So, for example, a network on chip with multiple clusters that run larger models and not models like MobileBert and similar.
Good. So, is there any other question folks you'd like to ask? Two questions are emerging in the chat. First one, how long did this project take, and how many people work on that?
Okay, so this work started with my master's thesis. So back in I think March last year, and this took around I think 6 months, more or less, yeah. And oh yeah, about how many people you think? 5 people seats? Yeah, I think 5 people. We were in the end working on this.
Another question I have here from Peter is, why did you rule out the lookup since BF16 would only need 128?
Oh, okay, yeah. So we didn't use a lookup table because still we have to store this as somewhere, and in the end using it will certainly be more accurate, obviously, but we will have to store every value of, of the exponential function, and in the end it was more convenient to to just create a small module that computed actually computed the correction over just building a lookup table. So it is more convenient, basically. Even though, the before 16 as a really short mantissa.
Okay. So folks, any more questions? We have time. Okay. Looks like we do not have any more questions. So, Andrea, I'd like to thank you again for joining, for presenting your work. The technical stack is open, so if you decide to share more knowledge, feel free to let us know. Thank you for your time. Thank you for presenting. The recording will be available, I believe, by the end of today or tomorrow on our RISC-V YouTube channel. And I'm going to reach you out to asking for a PDF of this presentation we can share with the audience.
Mm-hmm. Okay. So thank you for inviting me here, and have a nice day.
Thank you very much, Andrea. Thank you. Thank you everyone for joining. See you in the next technical session.